Hey there, chemists. We're going to start a unit on aqueous reactions in this video. That just means reactions that are done in water. We have a whole unit devoted to this because water is such a common solvent for many reactions we see in chemistry. So we're going to walk through the 3 different types of reactions, and today we'll start with one of them called precipitation reactions. That's the main theme of today. Before we get into a precipitation reaction, though, I want to review a vocabulary word called electrolytes. Electrolytes are things that conduct once you dissolve them in a solution. So these are salts and ionic-based things that have mobile ions once you put them in water. On your notes, I see strong versus weak electrolytes. And what that means for us, strong electrolytes are fully dissociated. So that's any soluble salt or strong acid or base. So soluble salts, which we're going to talk about today, as well as strong acids and bases, which are actually in a later lesson. For example, sodium chloride is a soluble salt. Hydrochloric acid is a strong acid. Sodium hydroxide is a strong base, and these all dissociate in water into separate ions, sodium and chloride ions, hydrogen and chloride ions, sodium and hydroxide ions, and it's the presence of those ions that allows us to have conduction. So if I had a beaker with one of those things dissolved in it and stuck a light bulb that was connected to a power source but broken apart, the circuit would actually be able to be completed just by being in contact with the aqueous media. As long as you have charges that can move, as long as you have mobile charged particles, you can have electricity, you can have conduction. This is different than a weak electrolyte. Weak electrolytes are only partially dissociated. So if I did the same experiment, I would see a very dim light bulb effect, because weak electrolytes are things like sparingly soluble salts or weak acids such as acetic acid, HC2, H3O2, or a weak base such as ammonium hydroxide, NH4OH. These dissociate, but we write them with reversible arrows because they only partially dissociate. Acetic acid does give off hydrogen ions and acetate ions, but most of it stays together as molecules. Even though it dissolves, it doesn't dissociate. Those are different things. Dissociation actually means it breaks apart into ions. Dissolving just means it goes into solution and you can't filter it by filtration. Ammonium hydroxide would obviously give you ammonium ions and hydroxide ions. So these are weak acids and bases. So, what's not mentioned here are things that are non-electrolytes. That would be things that just don't dissociate at all, because they stay as whole molecules. But we'll see examples of those later. So what I want to do is I actually want to focus for the rest of this lesson primarily on the soluble salts that we just talked about. How do we know if a salt is soluble? Well, the main answer to that is it's empirical. There are solubility rules that tell us when certain combinations of ions come together, you get a soluble salt. And I'm going to show you the main rules for the spectator ions. When do we have things that will always form a soluble compound? There are 6 rules that I'm going to give you, and they actually have an acronym starting with N, A, G, and S, A, G. NAG, SAG, easy to remember. And what does that stand for? Well, the N stands for anything that is a nitrate, which is an NO3 minus ion. A is acetate. Remember from your polyatomics, C2, H3, O2 minus. G is group 1, meaning group 1 of the periodic table. So sodium ion, lithium ion, potassium ion, etc. S is sulfate. SO4 2 minus. A is ammonium, NH4 plus, and G is group 17, meaning chloride, bromide, and iodide. And that covers almost all the solubility rules that you'll need for this class. If a compound contains a nitrate, an acetate, or a group 1, it is a spectator, and therefore it is soluble. I put them in this order not just because it gives us an easy acronym to remember, but also because there's a couple of exceptions to these, and it primarily comes at the lower half of this list. Sulfates are typically soluble, except with calcium, barium, and then 3 other heavy metals, silver, lead, and mercury. So sulfates are typically soluble in a compound unless they're with some of the group 2s or silver, lead, and mercury. The other exception to know is in the very last rule, the group 17s, chlorides, bromides, and iodides, except with silver, lead, and mercury. And those I can actually remember as a little cluster that seem to fall into multiple exceptions. You'll also notice I didn't put fluoride in here. Fluorides are often not soluble. However, they are if they're present with things like ammonium or the group 1 cations. There's no exceptions for nitrates, acetates, group 1s, or ammoniums. Those are pretty much exclusively going to be soluble. It's just the sulfates and the group 17s that have these exceptions. Now, there are much more extensive rules for solubility rules. Here's a abbreviated solubility rule chart, and you have one from the Regents reference table back in 10th grade as well, but it's a little bit too encompassing. I think it's better just to summarize when are things soluble, and if you follow the NAG-SAG, I think it'll be easy to remember which things are soluble. So let's practice that. Let's just look at these 6 compounds and classify, are these soluble or insoluble? And if you see a NAG-SAG ion and it's not an exception, it's soluble. I see nitrate, so this is soluble. B, magnesium chloride. Chloride is a NAG-SAG, and magnesium is not an exception, so this is soluble. C, nickel 2 hydroxide. I don't see a NAG-SAG ion, so I'm going to guess insoluble. And that's correct. Lead 2 sulfide. I don't see a NAG-SAG ion, so I'm going to guess insoluble. And we're right. Lead sulfide is fairly insoluble. E, magnesium hydroxide. Nothing from our NAG-SAG list. Insoluble. And likewise, iron 3 phosphate. Nothing from the list. So insoluble. And that's it. You're just scoping out and seeing, is there an ion? There's always 2. Is there at least one that's from our NAG-SAG list and not an exception? And if that's true, then it's soluble. Otherwise, you can pretty much guess that it's insoluble. What does this have to do with chemical reactions? Well, here's how we write precipitation reactions. Precipitation reactions are double replacement reactions where you have 2 compounds that start off aqueous, and you make 2 new compounds where they swap partners. So this is potassium ion and chromate ion, barium ion and nitrate ion, and that's what I actually have in solution. This is potassium ion, chromate ion, barium ion, and nitrate ion. And in theory, they would trade partners. The potassium would go with the nitrate, the chromate would go with the barium. But we only write the net ionic, which means we only include the things that aren't still in solution. Now, potassium and nitrate might pair up because of opposite charges, but those are both NAG-SAG ions. They would still be soluble. Chromate and barium, however, would not be a NAG-SAG combination. They would be insoluble, and that's the actual product. So I'm going to make barium chromate, and it'll be one of each. But I don't even have to write out all these ions. I could just look at the original starting materials and cross out things that I know to be spectators, and I'm left with just chromate and barium. I picture the charges in my head of what they are, and I simply write the product, barium chromate, and the reactants are the ions that form that in either order, Ba2+, and CrO4, 2-. That's the net ionic for that reaction. It's just the formation of the precipitate. So let's try another one. Silver nitrate and potassium chloride. I spy a NAGSAG nitrate. I spy another one, potassium. Chloride is a NAGSAG ion, but there's an exception with silver. So in this case, silver is going to form a bond with chlorine, and you'll make silver chloride. Silver chloride. So my net ionic is going to be Ag+, and Cl- produces AgCl. That's it. Everything else is a spectator ion. It's not involved in the reaction. So I'd like you to hit pause and see if you can come up with the other three as a net ionic. Cross out whatever's a spectator, and if there is a combination that's left, write out the net ionic reaction. Okay, let's take a look at number 4. We have potassium is a spectator. Nitrate is also a spectator, and then chloride is often a spectator unless it's with silver, lead, or mercury, but I don't see that anywhere. So chloride would also be a spectator. That means the only thing that's not a NAGSAG ion is barium, but there's nothing left for it to combine with here. So if you thought that there's no reaction in number 4, you are correct. No reaction. It's all spectators. You're just mixing the two together. But if there's no precipitate, there's no reaction. If there's no solid, there's no reaction. Number 5 should have a reaction. Sodium is a spectator, nitrate is a spectator, so we're left with sulfate and lead 2. So I would write the combination of sulfate, SO4 2-, and lead 2, Pb2+, takes 1 of each, and you always write the cation first when it's in the compound. As reactants, it doesn't matter, and there's our net ionic. Last one, KOH. K is a spectator. Iron 3 nitrate. Nitrate is a spectator, so we're left with hydroxide and iron 3. So I have iron 3 and hydroxide, and I'll form iron 3 hydroxide, ferric hydroxide. And notice in this one you actually need to balance. It takes 3 hydroxide ions. I don't balance it until after I've already written the net ionic. It's much faster than writing the complete ionic reaction with all these spectators. So that's how you write net ionic reactions for precipitation reactions. The product is just the solid, the precipitate, and the reactants are just the ions. Notice we're not putting phases in our reaction. It's implied when you see an ion, when you see a charge, it's implied that it's aqueous, so we don't need to write aqueous. And when it's neutral, it's implied that it's the state it would normally be in under standard conditions. So a compound that's ionic would be a solid for the most part. So this means aqueous plus aqueous makes a solid, and that's how all precipitation works. We were able to do that from our solubility rules for things that are soluble ions.